This is the Analytical Chemistry course review. This session is on experimental data and error. We will go through this fairly rapidly. You can stop the recording and return or review any of the information that you want to hear again. First, on concentrations. In most chemical applications, we use molarity as the units of concentration, which are moles of solute per liter of solution. And that's abbreviated with a capital M, or the square brackets also imply that we're using molarity as a concentration. In doing these calculations, it's important that you carry your units through so that you can keep track of whether or not you're talking about moles of solute, moles of solution, liters of solution, liters of solvent, and that you don't get confused on those various units. Less commonly, we also use molality, which tends to be somewhat confusing. It's abbreviated with a lowercase m, and it is moles of solute per kilograms of solvent. And this is one of the only concentration units where the denominator is solvent rather than solution. So in some cases, you have to go through multiple steps to get to the kilograms of solvent. You may have to use the density in order to calculate the mass of solution total, and then you can calculate the mass of solute, and the difference between the mass of the solution and the mass of the solute would be the mass of the solvent. So sometimes you have to break that down into multiple steps. Other applications outside of chemistry tend to use different units for concentration. Milligrams per liter or other configurations of that are common. In some medical applications, it may be milligrams per deciliter or micrograms per deciliter, but again, in that case, the numerator is referring to solute and the denominator is referring to solution. In environmental applications, we tend to use milligrams per liter, which is again milligrams of solute over liters of solution, and that can be equated to parts per million. And so those two units, milligrams per liter and parts per million, or ppm, are used interchangeably. And for ultratrace kinds of measurements, parts per billion is the same as micrograms per liter, and those can also be used interchangeably. Significant figures. For addition and subtraction, significant figures are limited by the number that has the smallest number of decimal places. So in this case, we're looking at 83.798 being the limiting factor. It only goes to 3 places to the right of the decimal place, and that's where we will truncate our final answer. It is based again not on the total number of significant figures, but on the number of figures to the left of the decimal place. If you're looking at numbers that don't have figures to the left of the decimal place, but only ones to the right of the decimal place, you may have to convert to scientific notation in order to accurately express the correct number of significant figures. In that case, if you're using scientific notation, you need to be sure that all of your exponents are the same. Because in this case, if you're looking at this first example that's to the left, it would look like all 3 of these have 3 figures to the right of the decimal place. But in fact, when you put them in the same exponent, you can see significantly different numbers of decimal places. So you have to first convert so that they're all to the same number of exponents, and then look at the decimal places. Again, so in this case, the 9.84 is what's going to limit the number of significant figures in the answer. You would get an incorrect answer if you used it with differing exponents. In multiplication and division, in this case, we are limited by the figure with the lowest number of total significant figures. So in this first example, they both have 3 significant figures, and the answer will also have 3 significant figures. In the second example, one of them has 5 significant figures, one has 2, and the answer is going to be limited to 2 significant figures in accordance with the smallest. And in this last one, the first one has 4 significant figures, the last one has 6, and so we're going to limit our answer to the 4 significant figures of that 34.6. In looking at logarithms, we've kind of got a completely different rule that comes into play. Remember that when we're looking the log of n equals a. That's the same as 10 raised to the a power. And when we get that answer, so the log of some number, such as 339, gives us a log answer, and that's broken into two parts. The part to the left of the decimal place is the characteristic. To the right of the decimal place is the mantissa. And our significant figures are going to be determined by the number that we're taking the log of, such as 339, and the mantissa. And in this case, those two numbers need to match. So if there's three significant figures over here that we're taking the log of, we're going to have our answer with three figures in the mantissa. That's illustrated a little bit better in the second example, where we've got the log of 3.39 times 10 to the minus fifth, and then you can see our answer is minus 4.470, and you can kind of see that the exponent and the characteristic are related to each other. So the characteristic tends to tell us what the exponent is, and the mantissa is the actual log of the number. So again, three significant figures that we're taking the log of, three significant figures in the mantissa. When we're going backwards and taking the antilog, we go just exactly the opposite direction. So in this case, the antilog of minus 3.42, in this case the minus 3 refers us to the exponent, and the 4.2 is the mantissa. So we're going to expect to have two significant figures in our antilog answer, and that's what we get over here in the 3.8 times 10 to the minus fourth. So the number of significant figures in the mantissa is going to equal our answer for the antilog, number of significant figures. All right, types of experimental error. When we're looking at an experiment and we're looking at the different places that error are introduced into the experiment, we know that there is error associated with every measurement that we take, every piece of equipment that we use, every solution that we use in lab. Every single small step of the experiment adds some kind of error. The first kind of error is systematic or determinate error, and that is a consistent error. The assumption is that systematic error can be tested for, it can be corrected, and it can be eliminated. So anytime you see a result reported from a commercial lab, the assumption is that all systematic or determinate error has been eliminated. The other clue to this is that consistent error tends to be consistent in either positive or negative direction. So it means my balance has been calibrated incorrectly, and every mass that I take on that balance is consistently high or it's consistently low. Or I have a reagent that is contaminated, so every time I use that reagent, my measurement is either consistently high or consistently low. I have a crack in the case of my spectrometer, which is letting in stray light. So every measurement taken on that spectrometer is consistently affected by the amount of stray light that enters. This error is different from random or indeterminate error. And random error tends to be analyst error, and we can control it to some extent by improving skill and improving procedures, but there's no way to eliminate random error completely. So it's where you splatter a solution when you're transferring it. There is powder on your balance pan when you take a measurement that affects that mass. Your meniscus on a particular reading is either high or low from where you're reading it. You punch a number into a computer or into a spreadsheet incorrectly. Random error is random. It doesn't consistently fall to the high side or to the low side. It has an equal chance of being either positive or negative. The other thing that we're interested in looking at our data is precision and accuracy. Precision refers to the reproducibility of our data. If I take one single sample and I analyze it by the same method 10 different times, how close are those 10 different results are going to be? How close are those results? Can I reproduce the results? Do they fall within a tight cluster? Statistically, we measure that with the standard deviation. Accuracy refers to how close my measurement is to the true measurement, to what it is supposed to be. In an analytical lab, we can measure that sometimes by looking at a certified sample. If I measure a sample that I know the concentration of, how close do my measurements come to that true known value? Okay, it's akin to the mean, but it's not. Accuracy and the mean are not the same thing. Again, what we would be looking at is how close is the mean that I obtain in an analysis to the value that I expect or that I know to be true. And precision and accuracy tend to be looked at classically with a bullseye. You can see in this first bullseye that you have a really large scatter, which means the results were not very reproducible. One was far off to the bottom, one was far off to the top. They're not systematically high or low, but they're randomly very far scattered. And if you look at the center of these, it's not necessarily going to be right at the bullseye. So this first example has neither precision nor accuracy. In the second case, you can see the scatter is somewhat less, but it's still fairly high. However, it is clustered fairly close to the bullseye. So again, precision's not great, but accuracy is better. It's getting close. So if I look at the center of this scatter, it does come close to the bullseye. So it's accurate, it's just not very reproducible. The third case over here is the ideal. All of the dots are close together, which means they're very reproducible. We can do the same thing over and over and over again and get the same results, and they're scattered right towards the center of the bullseye, so they're very close to the truth. So this one is both precise and accurate. And in the last one, again, we have very reproducible results. Every time we shot at the bullseye, we got close to the same thing, so we can reproduce our results, which means the precision is very good. However, the cluster is not around the bullseye, so it's not very accurate. So in this case, we have high precision but very low accuracy. Okay, that's the end of this section. You do have the review booklet. The review booklet gives you a little bit more written information about this, and it does give you some review problems that you can use to test yourself.